page 5 of Eulers and complex numbers for HL. So argument in polar form. On the page 487 reading, we see that the complex number z is broken into the real and imaginary components a plus bi, and you can express that as a vector ab. The angle theta that the vector makes with the real axis is called the argument of z, or argz. That's like an angle. It's measured similarly to the way the angle of the unit circle is measured. In order to eliminate ambiguity, the domain of theta is defined to be negative pi to pi. You can see that this is not inclusive and this is inclusive. So if you have an 180-degree angle, then you would call that pi and not negative pi. Real numbers have arguments of 0 or pi, right? So like positive numbers would have an argument of 0, and negative numbers would have an argument of pi. Purely imaginary numbers have arguments of pi over 2 or negative pi over 2. If the hypotenuse is defined to be length r, then we can define a complex number in terms of r and theta. So we have here r and r multiplying, scaling the real component and the imaginary component. And the real component and the imaginary component are trig proportions of the angle theta, because when you draw the unit circle triangle, remember that if you have an angle of theta, the x component is cosine of theta if it's a unit circle, and the y component is sine of theta. But if the hypotenuse happens to be r, then it would be r cosine of theta and r sine of theta. You could also write it like this by factoring out the r. If r is the magnitude or the modulus of z, and we create the notation cis comes from the c here, the I here, and the s here. So we can redefine z by putting modulus of z instead of r, and instead of writing cosine theta plus I sine theta, we can just write cis theta, because it's a notation which abbreviates cosine theta plus I sine theta. The conjugate of z has the same modulus, but its argument is negative theta instead of theta. Okay, right in polar form. Okay, so we got 4 is just a positive real number. So the cis value would just be 0 degrees. Okay, so we would have 4 cis 0. What about negative 6? Negative 6 is magnitude or modulus of 6, and the cis value would be negative pi or pi because it's extending to the left, right? 4 cis 0 is 4 units to the right. Negative 6 is 6 units to the left, also known as 6 cis pi. 1 plus I, that would be 1 unit here and 1 unit here, 1 unit in the real direction, 1 unit in the imaginary direction. So obviously the cis value is the argument is going to be 45 degrees or pi over 4. And the magnitude is going to be square root of 2, because if we use Pythagorean's theorem, we know that the magnitude of the hypotenuse in this case is square root of 1 squared plus 1 squared, square root of 2. For this one here, we're going to go negative square root of 3 in the left direction, and then we're going to go up by 1 in the imaginary direction. Oops, I drew that kind of in a misleading way. That's actually going to be a flat triangle, not a tall triangle. So that would be a 30, 60, 90 triangle, and that would be the 30 degrees here, so it would be 150 degrees. If we were to write that in terms of, radians, we would write 5, 6 pi radians. And let's see, this is a 30, 60, 90 triangle, and this short side is 1, so that means the hypotenuse would be 2 long. So we would write 2 cis 5, 6 pi. Number 3. Convert k plus ki to polar form. You must consider k is greater than 0, k is equal to 0, and k is less than 0 cases separately. So let's first assume that k is positive. If k is positive, then a k-sided triangle is going to have a cis value of 45 degrees of pi over 4, right? And the magnitude is going to be square root of k squared plus k squared, which is going to be square root of 2 times k. Okay, that would be the magnitude because of the proportion of 45, 45, 90 triangle. What about the case where k equals 0? If k equals 0, basically that means that the hypotenuse is 0, which means it's just 0. So in that case, you would write, I don't know, 0. I think you would just write 0. You could write 0 cis 0, I guess, but you know, it's kind of meaningless because the magnitude is just 0. The modulus is just 0. What about the k is less than 0 case? This is interesting. This would be negative k, or negative number plus negative number I. So that would be pointing into the third quadrant like that. And so this length would be k, and this length would be k, and this length would be square root of 2 of k, just like we found in the first part. And the angle would be 180 degrees plus 45 degrees, which would be pi plus pi over 4, which would be 5/4 pi. So the cis value is 5/4 pi, and the modulus is going to be square root of 2k. Okay? Number 4, we're going to convert to Cartesian form without using a calculator. So we got 2 cis pi over 2. So we have a 90 degree angle, so that would be like that, and the length of the vector is 2, so it's just pointing straight up like that. If we were going to write this in Cartesian form, it's pointing in the imaginary direction, so it would basically be real part 0 plus imaginary part 2i. For this one here, we're looking at an angle of pi over 6, 30 degrees, and the modulus is 4, so the hypotenuse is 4 long. If this is a 30, 60, 90 triangle and the hypotenuse is 4 long, then this side would be 2 and this side would be 2 square root of 3. So if we want to convert this into a plus bi form, then it would be 2 square root of 3 plus 2i. Last one. Now we're at 2/3 pi, which is about like that. Okay? And so the modulus is square root of 3, which means that, let's see, let me erase this, it's in the way. The modulus is square root of 3, and this is 60 degrees here. So if this is square root of 3, then this, the bottom part, would be square root of 3 divided by 2, because it's half of that, and then the vertical part would be square root of 3 over 2 times square root of 3, which would make this 3 over 2. So in this case, we got negative square root of 3 over 2 for the real part, and the imaginary part would be I times 3/2. 5a, find the value of cis 0. Cis 0 would just be a angle, and what's the modulus here? The modulus here is 1, right, because we can't see any number there. So it would be a vector of length 1 pointing in the right direction, in the 0 degree direction. So that would be basically 1 plus 0i, or just 1, right? Find the modulus of cis theta. Okay, so the modulus of cis theta is, let's see, we're going to draw a picture just to help us out with that. So we got theta here. We got, and cis theta is a magnitude of 1. And then the x component would be cosine theta, and the y component would be sine theta. So if we wanted to find oh, we already found the modulus. The modulus is 1. I was going to say we could take the square root of cosine squared plus sine squared, but cosine squared plus sine squared is 1, so the square root of 1 is 1. So the answer is just 1. Show that cis alpha times cis beta equals cis alpha plus beta. Okay, so for this case, let's expand it out. Okay, so if we have cosine of alpha plus I sine of beta, or sine of alpha, for cis alpha. And we have cosine of beta plus I sine of beta. And we do FOIL on this, we're going to end up with cosine alpha plus, cosine alpha cosine beta. And then for the inner product, we have I sine alpha cosine beta. And then we also have I sine beta cosine alpha. And then we have I times I, which is -1, so we end up with negative sine alpha sine beta. Okay? And then we're going to group the real parts together, and we're going to group the imaginary parts together, and then we're going to use, like, you know, those trig identities with the sum and the product or whatever. So we're going to have cosine alpha cosine beta minus sine alpha sine beta. That's the real part. And the imaginary part is I times sine alpha cosine beta plus sine beta cosine alpha. And so cosine alpha cosine beta minus sine alpha sine beta, that is the trig identity, cosine, the sum of a cosine, or the cosine of a sum. So cosine alpha plus beta. And then it will be plus I, and the trig identity for this one is going to be the sine of a sum. Okay, that's it for page 5.